Okay, I'm going to have you try this one. Let's say that we have a proton that's going from east to west. It experiences a magnetic field going out of the board, out of the page, and you can figure out which way it's forced. So go ahead and draw this out. Use the screen or use your sheet of paper and write down what direction you think the force is. And once you've done that, you can continue. So go ahead and hit pause and try that, and when you're ready to check, you can hit play. All right, so you should have pointed, if you use the computer screen, you should be pointing to your left, and then your middle finger should be coming at your face, and then the force would be up the page. If you use your sheet of paper, you should be pointing to the left side of your sheet of paper, your middle finger should be coming out of the paper, and your thumb should be pointing towards the top part of your paper. All right, so magnetic field causes force on charged particles. Forces can be measured, and the right-hand rule will be able to figure out the direction of the force. And so, if you get your right-hand rule ready, you put your hand in that position. FVB, just think, your thumb is force, pointer finger is velocity, magnetic field is your middle finger, FVB, and you should be able to remember that. The way that we calculate this is based on three factors. How much charge do you have? How fast is that charge moving? And what is the strength of that field? And then what component of that is perpendicular to that field? So the charge in coulombs, velocity, or the speed really in meters per second, and then the strength of the field in Tesla. The angle represents the angle between the velocity or the speed and the magnetic field. And I guess really with the direction, you have the velocity there. And the biggest thing is to keep an eye on how much is it perpendicular to the field. Is it if it's actually aligned with the field, there's no force, right? If it's perfectly aligned with it. But if it's at a 90-degree angle, you're going to have perfect amount of force. So I'm gonna have you try this one using the right hand rule as well as calculating this. Let's say that we have a force exerted on a 3 microcoulomb charge, positive, moving north at 300,000 meters per second, and a magnetic field of 200 millitesla. And let's say that the field is directed north in part A, the field is directed south in part B, the field is directed east in C, and then west in D. And yeah, let's try that. So go ahead and pause the clip and work through all 4 of these, calculate each one, and then also use the right-hand rule, and let's see how you do. All right, so for part A, if this is moving north and the field is moving north, this would be sine of 0 degrees. There's no force. So the velocity is north, the field is north. No deflection. In B, if the particle is moving north, but the field is going south, this is 180 degrees. So again, sine of 180, this would be 0, so there's no force on it. In C, we would have, our pointer fingers pointing at the ceiling. Our middle finger is going to our right wall, and then our thumb is into the page or into the screen here. So the force would be down. In part D, we're pointing towards the ceiling. Our middle finger is going from right to left, and our thumb should be pointing at our face. So the force would be up. And then that amount of force in C would be 0.18 newtons into the page, or in D, it would be 0.18 newtons out of the page. How about this one? Let's say that our particle is at an angle to the field. This particle is going 300 meters per second, 300,000 meters per second at an angle of 34 degrees, and we want to figure out what the force is on the particle. And so on this one, you're going to calculate it, but also use your right-hand rule to see if you can figure out the direction of the force. And so go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so if we orient our hand, we should be pointing, kind of towards the top left, and then the field is going to the bottom left, and the force would be out of the page. Your thumb should be pointing at your face. And the amount of force would be 0.10 newtons. All right, so let's say we've got a proton going from west to east, and our field is coming out of the page. And we'll just practice this one. So go ahead and work this one out, and when you're ready to check, you can hit play to continue. All right, so what should be happening on this one is you should be pointing to the right wall. Your middle finger should be coming, actually, if you're holding your arm like this, you're pointing at your right wall, and then your middle finger is going to your back wall, so behind you, and then your thumb should be pointing at the floor, and the force would be first would be towards the bottom of the page, towards the floor. Now, what we have with the right hand rule, with a negative charge, if you know, our object is coming into let's say we have an electron, it's encountering the field and it's being forced. Yeah, we can figure out, you know, what the direction of, or what the force is. And what we do is we pretend it's a proton, and use the right hand rule, and then determine the force, or then when the force is opposite direction. Okay. So let's draw this first one out. Let's say we have an electron that's moving from left to right, and our field is going into the page. And we want to figure out what force it'll experience. And so we pretend like it's a proton. We figure out the direction of the force, and then the force is opposite for proton. So go ahead and pause the clip and try this one. Orient your hand to get that, and then when you're ready to check, you can hit play to continue. All right, so what'll happen is you should be pointing towards your right wall. Your middle finger should be going into your screen, and the force on a proton would be towards the ceiling. However, it's an electron, so the force would be towards the floor. Let's go ahead and try this one. Let's say that an electron is going into the page, into your screen. The field is going towards the floor, and you want to determine the force on it. And so, yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so to orient your hand, you should have pointed into the screen. Your middle finger should be going towards the floor. And a force on a proton would be to the left, but because this is an electron, the force would be to the right. Why don't you try this one? Let's say the field is going out of the page, and proton is going to the right. So go ahead and try this one, and then when you're ready to check, you can hit play to continue. All right, so okay, so you should point towards the wall. Your middle finger is coming towards, you're pointing towards the right wall. Your middle finger is going towards the back wall, and your thumb should be pointing downwards, so the force would be down on a proton. All right, so you know, all right, so let's take a look at a situation where we have a charge going into a uniform field. So let's say our field is out of the page here, and we'll make a bunch of dots. And let's say we have a proton here, and it's coming into this field, right? So again, if we orient our hand, we're pointing towards the right. Our field is to the back wall behind us, and the force would be downwards, right? So when this starts to come in, the force would be like this. Now, what's going to happen is it's going to start to come around like this, right? So if we continue to orient our hand, we're going to be pointing a little bit more downwards. The field is out, and at this spot right here, the force would be like this. And then if it continued, the force here would be like this. And so the force would actually make it so that it would start to go in a circle. And then it would continue in a circle if it was a uniform field. These magnetic forces are always right angles to the plane established, right? And you know, you can accelerate the particles. In this case, it'd be centripetal acceleration if it went entered a uniform field. And it could go in a helical path as well, right? If it's not perfectly lined up, you know, in that last situation we had the field like this, But let's say that, it's this proton is not only going this way, but let's say it's coming out of the page a little bit like this. What could happen when it encounters the field? It could be starting to go in a loop fashion, still coming out of the screen, but going in a circle as well. Magnetic forces cannot change the speed or kinetic energy. That's because it's acting at a right angle, right? All it's going to do is it's just going to change the direction of it. And that is an acceleration, right? Because the velocity is changing, but it's not speeding up or slowing it down. That's where you need the electric fields. Electric fields can speed up or slow down particles because they act in the same direction of it, right? Parallel to the motion. But with magnetic fields, they're acting in a 90-degree angle or a portion of that. And so, it's just changing the direction. So they can't do work, right? They're just going to be changing the direction. So these forces are centripetal. Remember, a centripetal acceleration is v squared over r. And centripetal force is therefore mv squared over r. And we can take a look at a situation here. Let's say we have, a velocity going to the left and the field is coming out of the page. And so let's orient our hands. Go ahead and take your right hand and point towards the left side of the screen. Your middle finger should be coming at your face. Your thumb should be going up then. And then what will happen is eventually it'll come around to the top. And let's try that one. We're pointing towards the right. The middle finger is going to the back wall, and then the force would be downwards. So the force would be like this. And then if it's over here, the velocity is towards the floor, the middle finger is towards your face, the force would be inward, and so on, right? The force is going to stay inward, and this is centripetal force. And what is actually providing that force, right? Well, that's QVB sine theta, right? QVB sine theta. That's the force, the magnetic field force, providing the centripetal force, right? And then that equals mv squared over r. And we've got that, right? That's the centripetal force, and we can find that. So what's the orbital radius then of a proton that's going at 20,000 meters per second, perpendicular to a 40 Tesla magnetic field? So why don't you go ahead and try this? You can pause the clip, go ahead and draw this out, and we can try that. And this is the orientation I want you to try. Let's say the field is going into the page and the proton is going like this. So go ahead and determine the direction of the loop, and then also the, in this case, how big the radius would be. All right, so let's see how you did. The particle is going to be going in. The centripetal force is caused by the magnetic field, QVB sine theta. And we should get 5.2 times 10 to the negative 6 meters. And if we look at the field going into the page, we have our particle, proton. So we should point towards our left. Our middle finger should be coming out of, or into the page rather. So middle finger towards the screen, into the screen. Our pointer fingers to the left, and so the force would be down once it's in here, the downward like that, and then it'll cause it to go in a loop that is counterclockwise.